AP Calculus BC, welcome to Off-Campus Learning Day. Let's pick up where we left off. By the time you finish watching this video, you will know what the assignment is that's due on Friday. You already know that homework 4.5 is due on Friday. There is an additional assignment that's due on Friday that will be paper submission, so listen carefully to the video and you'll find out what that is. So this is where we left off. If you have a son or a daughter someday and you want to celebrate your son or daughter's second birthday, just remember that it's the area under the sine curve from 0 to pi is exactly 2. So here's my recommendation for birthday number 2. On the birthday cake, just ask the person at the bakery to write the integral from 0 to pi of sine x dx, because that's a great way to represent the number 2. So let's go on to the next page. We had my daughter's first birthday. Happy birthday, Elia. Now let's look at number 8. There's an absolute value there. The asterisk means draw it out. So let's draw this one out. We've got a vertex at 3. So the absolute value function of absolute value x minus 3 from 0 to 5, this would be kind of like a situation where the velocity is absolute value of x minus 3. We want to find the total distance traveled. And so we want to find the area of this triangle plus the area of that triangle. And sometimes you can just say, hey, forget it. I don't need any calculus, because you know what? I know a formula for finding the area of a triangle. It's 1/2 base times height. So you can ditch calculus and just find the area of these two triangles. I mean, come on. It's 1/2 base 1 height 1 plus 1/2 base times height for the second triangle, 1/2 base 2 height 2. So even though you know all this fancy calculus now, doesn't mean you have to use calculus. It's 1/2 times, this first triangle is 3, base of 3, height of 3, base times height. And the second triangle is 1/2 times base times height. That's a base of 2 and a height of 2. So it looks like it should be 9/2 plus 4/2 is 13/2. Let's see if the calculator agrees with us. If we were to type in all the fancy calculus symbols, and we do have continuity on the interval 0 to 5, so we should be able to do this. So here we go. What if we type in the calculator integral from 0 to 5 of absolute value of x? Here, we can do that. We can go to Math 9 and type in the absolute value function by going to Math Number ABS. Absolute value of x minus 3 with respect to x from 0 to 5. We predicted that the answer would be 6.5. The answer is, notice it just gets an approximation. The calculator is not quite as good, but it does give us evidence that our 13/2 or 6.5 is correct. So watch out for opportunities to use geometry instead of calculus. How about the integral from 0 to 2 of 2t minus 1? Now there it's going to be maybe a little bit harder. Let's draw the graph of this. However, let's use calculus instead of geometry to do this one. Now 2t minus 1, just in terms of getting an accurate sketch, which you're not required to do, but let's do it. So 2 times the quantity t minus 1/2 is inside the absolute value. And the absolute value of a product is the product of the absolute value. So factor out a 2, get 2 times the absolute value of t minus 1/2. So what this means is that we have an absolute value graph. It's a V-shaped graph with a vertex at 1/2, which you could have figured out by just setting 2t minus 1 equal to 0 and solving for t to get t equals 1/2. So a little bit of a sketch on this means that at 1/2 there's a vertex, and we do have slopes of 2 and -2, but we're going from 0 to 2. So we are trying to find the area represented by the area of this triangle plus the area of that triangle. And the idea here is that for t values greater than 1/2, the value of this blob is going to be this expression. Blob just means expression in this case, 2t minus 1. So it can be positive. For t values less than, it's negative. So we take 2t minus 1, shed the absolute values with impunity for t values greater than 1/2, but we take the absolute value of a negative number to get its absolute value. So this is really going to be broken up into two problems. From 0 to 1/2, we're going to take the opposite of the blob. But from 1/2 to 2, the value of this expression is positive, so we're just going to take the blob as is, 2t minus 1 dt. Now, for the sake of time, that's as far as I want to go with this problem. I just want to show you what the setup would be. The absolute value problems often have to be broken up into two or more parts, where any part that corresponds to positive values, we leave them without the absolute value, and if there are negative values for the expression, we have to take the opposite. So that's a setup, and then you can go from there. Now, by the way, the reason that we're asking you to draw cosine x from 0 to pi is so that you can see quickly that the answer is going to be 0. Because isn't the cosine graph from 0 to pi equal positive directed area as much, well, the amount of positive area is equal to the amount of negative area. So you can tell the answer is going to be 0 just by your graphical intelligence. Now, if you didn't believe that and you actually wanted to see if calculus gives you a 0, geometry gives you a 0. Does calculus give you 0? Remember, the antiderivative of cosine x is sine x evaluated from 0 to pi. So it's going to be sine of pi minus sine of 0 according to the fundamental theorem of calculus, which is also called the evaluation theorem. Sine of pi is 0, sine of 0 is 0, so you get 0. Either way, you use your graphical intelligence or the fundamental theorem of calculus, then you get 0. Again, the fundamental theorem of calculus is also sometimes called the evaluation theorem, because it's a theorem that helps you find the value of a definite integral. Find the value of the definite integral. Okay. Number 11, find the area. Now it doesn't say directed area, it says just pure area. So if you want to find the area bounded by the graph of this line and the x-axis from 0 to 10, let's draw a picture of the situation. This is a line with slope 1, y-intercept -3, so slope of 1. And it would be a mistake to think that the answer is the integral from 0 to 10 of x minus 3 dx. That's a mistake. Because it doesn't, because we have to treat this as positive area. And the area bound by the graph in the x-axis requires this be treated as positive and that be treated as positive. So this is not the right way to go. You could fix that. You could fix the mismatch between this representation and this problem by either taking the absolute value of x minus 3 or just saying, look, I'm going to take the opposite of the area from 0 to 3, this is the x-intercept is 3, of x minus 3 dx, because I can see that calculus will give me a negative area here, and I want the opposite of that negative area. And then when I go from 3 to 10, I'm going to take the area as is. This is just a setup. You have to do calculus to get the final answer, but oftentimes the hardest part of these problems is the setup. So let's go to the next page. And now we're going to look at U substitutions. We're going to mix U substitution lesson with this lesson. And that's going to require the use of a new concept. So get ready. This is going to be something new. We've done U substitutions, but never with the fundamental theorem of calculus. I'm inclined to let U equal 1 minus x squared here. And so du is going to be negative 2x dx. I'm going to doctor with a negative 2, counterbalance with a negative 1/2. So far, it's all review. We get negative 1/2 times the definite integral from, and here's the new part, whenever you use a U substitution with a definite integral, you are required to do this thing which you've never done before. It's called converting the limits of integration. We have to convert the limits of integration because these are currently probably haven't thought about this very much in the past, but these values of 0 and 1 are values of this variable. So that's from x equals 0 to x equals 1. We're now converting this integral from x to u, and unlike what we've done in the past, we're going to leave it in u. There's no reason to come back to x. We're going to go from x to u. We're going to say goodbye to x forever in this problem, once it becomes a du problem. And right now we have negative 2x dx, which is du. We're not going back to x. We're going to leave it at u. And this is the square root of u. So we got square root of u du. We've done it. So that means we're going to have to convert these numbers from values of x to values of u. And we're going to use this equation to do it. You see, when x is 0, the corresponding value of u is 1 minus 0 squared, or 1. And likewise, when x has a value of 1, let's convert the upper limit of integration from an x value to 1 minus 1 squared is 0. So now we have a significantly less complicated problem. We know how to find the antiderivative. This is going to be negative 1/2 times the antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2, or times 2/3. And that's going to be evaluated from 1 to 0. By the way, let's simplify that. I'm going to bring the negative 1/2 in. So that's going to be negative 1/3 u to the 3/2 evaluated from 1 to 0. That means I'm going to put a 0 in for u first. So it's negative 1/3 times 0 to the 3/2 minus negative 1/3 times 1 to the 3/2. That's just 0 minus negative is positive. So we've got 1/3, because 1 to the 3/2 is 1. I believe the final answer is going to be 1/3. And let's confirm that on the calculator. Would you please take some time now to type the original problem into your calculator to see if it works? I'm going to pause it. You go ahead and type it, and then we'll see if they are the same. Okay, I typed in the original problem. It's x squared 1 minus x squared, comma x, comma 0, comma 1. I got what it amounts to. It's pretty close to 1/3. It's actually exactly 1/3. So now I would like you to attempt problem 13 on your own. I'm going to try it here, and then when we're done, we'll compare. So try 13 all by yourselves. Remember to convert the limits of integration from values of x to values of u. You may begin. All right, I'm almost done with this one. My u substitution was 1 plus 2x squared. Du is 4x dx. So I doctor with a 4, counterbalance with a 1/4. I converted the limits of integration using this equation. So when x is 0, u is 1. When x is 2, 2 squared is 4 times 2 is 8 plus 1 is 9. So did you get new limits of integration? Instead of 0 to 2, did you convert those to 1 to 9? That's what you should have done. So now it's 1/4 integral 1 to 9 of u to the negative 1/2 du. So take the antiderivative using the fundamental theorem of calculus. I've got u to the 1/2 divided by 1/2, or times 2 from 1 to 9. So I'm just going to write it out like this. Keep the 1/4 out there. It's 2 radical 9 minus 2 radical 1. So to finish it up, I've got 1/4 times 2 times 3 minus 2 times 1. And that becomes 6 minus 2 is 4. It's another way to celebrate your firstborn's first birthday, or maybe your thirdborn's first birthday. This should come out to 1. And if we go to the calculator, we should get x over the square root of 1 plus 2x squared. So let's see if I can remember that. Actually, I'll put it on the bottom so I don't have to remember it. So the calculator, when I type in math 9, of x divided by the square root of 1 plus 2x squared, close the square root, comma x, comma 0, comma 2, I should get the number 1, and whoa, that's correct. So great way, it's actually kind of a boring way to celebrate your daughter's first birthday. Now, let's keep on going here. Next one, this one's interesting. These are the sorts of problems that we see on the AP test every year, and students get flummoxed by them. They're like, what? But if you know the fundamental theorem of calculus, in fact, these problems are fancy ways for test authors to see if you really understand the fundamental theorem of calculus. So let's take a quick look at how to use the fundamental theorem of this. I don't know what f of x is, but I know the answer is 20. So that means that there's some function, some antiderivative of f, I'll call it capital F, evaluated at 12 minus capital F evaluated at 4, that's giving me 20. So that's one thing I know about this. Now, notice that these are the same letter. This is another function, f of x. And I tell you, if I were to do a u substitution, I would let, even though, just try it. Let's go with this. Let's let u equal 5 minus 2x. If u is 5 minus 2x, then du would be negative 2 dx. So I can convert this limit of integration from an x-based integral to a u-based integral. And using this as my translation guide, I'm going to put an x value of 1/2 in for x. I get 5 minus 1 is 4. So this is going to be from u equals 4. Oh, what a coincidence. It matches that. Up to, and I just realized I skipped the part where you convert, where you doctor and counterbalance. I don't have a negative 2 dx, I just have dx. So I've got a doctor with a negative 2, counterbalance with a negative 1/2. Okay, let's convert the upper limit of integration. If I put in x equals negative 7/2 into this equation, the corresponding value of u is, let's see, what's negative 2 times negative 7/2? That'd be negative 2, so that'd be positive. And it would be 7, 5 plus 7 is 12. So f of u du. Now, what we see here, the negative 1/2 has to tag along because I doctored with negative 2, so I counterbalance with negative 1/2. So what I'm looking at here is a problem that is pre-cooked, because when you do a u substitution and convert the limits of integration, you get a very happy coincidence. This matches up with that. I mean, this one's f of x, this one's f of u du. It doesn't matter what the letter is. The point is, when you put a variable into the f function and evaluate it from 4 to 12, you get 20. So negative 1/2 times 20 is negative 10. So it turns out that this fact over here, we ended up not using that. I mean, it is true, but I was just playing around with that in case we needed it. What we really needed to do was convert the limits of integration upon a u substitution. Okay, let's go to the next problem. Okay, yeah, this is an important one. Okay, problem 15. Okay, find f of 6. They're telling us f of 3 is 2, and the integral from 3 to 6 of f prime of x dx is 8. So these problems tend to seem kind of confusing. However, what they're really doing is going back to what we did on day 1 of this lesson, where we said final position equals initial position plus net change in position. They've given you enough information in this previous problem to use these words. So what I'd like you to do is write final equals initial plus net change. Like, what is it? Final position, final velocity, final acceleration? Well, we don't know. That's not specified. It's not a real world problem. But we can say that in this problem, we start at time 3. We start at time 3, we could say final position, initial position, net change in position. We could do that. We could superimpose a real world context just to help our minds grasp the problem. So it looks like we're going from time 3 to time 6. So time 6, that would be the final position. So it could be f of 6. F of 6 can be found by taking f of 3 plus, and then all of the change that occurred from the initial position to the final position would be the integral from 3 to 6 of f prime of x dx. This is remarkable because they gave us f of 3. They told us we're starting out at position 2. It's like we're starting out at mile marker 2 on the interstate. And then that was at time 3. And then here we're going to add up all of the, so f prime, that would be velocity. If f is position, f prime would be velocity. So it's like, let's find the net, the displacement. That would be the net change in position. So let's find the displacement from time 3 to time 6. So this is a kind of problem where I've been preparing you for days by setting up these boxes. But if you understand that some of even the most complicated looking problems in calculus can be reduced verbally to final equals initial plus net change, then you're probably going to get a 5 on the AP test. I mean, this alone, if you can spot this, these are problems that nationally very low percentages of students get these correct. But just f of 6 is what they're asking for. It's f of 3, which is 2, plus that, which is 8. The answer is 10. F of 6 is 10. There's nothing more to it than that. So final equals initial plus net change. When I say go, I'd like all of you to say out loud and in unison, final equals initial plus net change. Ready? Go. Final equals initial plus net change. Wow, will that ever come in handy? Okay, next, number 16. Okay, here we go. Absolute value, we're going to have to use our pre-calculus skills of graph sketching. A little bit of pre-calculus work here. X squared minus 4x plus 3. Hey, that thing factors. That shit factors into x minus 3 times x minus 1. Sure enough, minus 3x. I found it. I found the factorization. So that means that the x-intercepts of this parabola are at 1 and 3, and it just kind of goes like that. The parabola has some positive area, some negative directed area, and then some positive. But they're asking for the absolute value of this function, which means that the part here that was dipping down is going to have to be reflected up. So it's really going to be 3 positive regions right there. And by symmetry, these two are going to have the same area. We'll say this blue one is going to have the same area as this blue one over there. So we need 2 blue areas and a yellow area in order to make sense of this. So to get rid of the absolute values, I'm going to have to lean heavily on this graph. I'm going to have to take 2 blue areas, so 2 times the integral from 0 to 1 of x squared minus 4x plus 3 dx. 2 of those. And then to get the yellow area, which I'll do that in orange up here. I won't torture you with yellow. Okay, so orange. I'm going to have to take the opposite of the integral from 1 to 3 of x squared minus 4x plus 3 dx. Why the opposite? Because when I take away the absolute value, the area under the curve from 1 to 3 will be a negative number. Just like when your velocity is negative, think length times width. Rate, distance is rate times time. So the rates are gonna be negative because the velocity went negative times time. That's gonna be negative area under there. So this would be the setup. I'm not gonna finish the problem because I know that once you get rid of the absolute values, you know what to do from here. It just takes time. So next, let's go to problem 17 in this lesson. Find total distance traveled from, okay, whoa, hold on. Okay, now we gotta think because they're giving us acceleration is 2t. V0, the velocity at time 0 is 6 meters per second. All right. This is like 5 giant steps. Okay, this is gonna be 5 baby steps forward, or maybe like 1 big person step forward on this. I'm just gonna lead you through it. There's a lot to it, right small. We start out with the acceleration at time t is 2t, okay? Total distance traveled, remember how we did total distance traveled. That would be the integral from 0 to 10 of the absolute value of velocity from time 0 to 10. So they didn't give us velocity, they gave us acceleration. Displacement would be the integral from 0 to 10 of velocity without the absolute value, 0 to 10 of v of t dt. And position at time 7 will be, I'll use p for position at time 7. So that's what they're calling for. They didn't give us velocity, they didn't give us position, they gave us acceleration. Okay, so here's what I'd like you to do. I'd like you to write acceleration as the derivative of velocity with respect to time. That's just another way to think of acceleration. It is the first derivative of velocity. dv dt equals 2t. Okay, next we're going to use this. This is a differential equation because it's an equation that has a derivative in it. So we are going to use a technique for solving a differential equation called separate and integrate. Separate and integrate has 2 steps. Step 1 is the separate part. Step 2 is the integrate part. So let's separate one variable on one side, the other variable on the other. We'll put 2 variables are v and t. We'll go v's on the left and t's on the right. So it's almost as if you have dv over dt. And it's like we're going to multiply both sides by dt. If you multiply both sides of this equation by dt, you get dv equals 2t dt. The separate part of separate and integrate is now complete. Now let's go to the integrate part of separate and integrate, which involves a swoosh, an antiderivative symbol on the left and an antiderivative symbol on the right. We have an empty canoe. It's like the antiderivative of no one's home, dv. But when no one's home, we know that's really what number? It's the number 1. The antiderivative of 1 dv. So notice I put the semi-permeable membrane right here as if the 2 has already passed through the membrane. So on the left, we've got antiderivative of 1 dv is v plus our first constant, right, c1, equals 2t squared over 2 plus our second constant of integration is c2. Right small. Now, C1 gets SpongeBobbed into C2 because constant minus a constant is a constant. So let's record the SpongeBobbing that has occurred. SpongeBob is actually not an official mathematical word. SpongeBob is informal expression. So when you subtract C2, rather C1 from C2, you get another constant. which we will just call C3. So V equals t squared plus a third constant, C3. So there's a whole family of velocity curves. Woohoo! Now we know which family to pick. We're going to solve for C3 by saying that, look, when velocity, or at time 0, the velocity is 6. So let's solve for C3. I'm going to document what I'm doing here. Solve for C3. By putting a 0 in for t. So V, oh, and by the way, a 6 in for velocity. That's what this says. This is called a set of initial conditions. When time is 0, velocity at time 0 is 6. So I'm going to replace V with 6 and t with 0. So C3 is 6. Hey, I've just found my velocity function. The velocity function is t squared plus 6. Whoa, we're halfway done getting to position. I want to get to position. I started with acceleration. It's going to be a two-part journey. The first part of the journey is to get from acceleration back to velocity by taking an antiderivative. I mean, think about it, it makes sense. If you take the derivative of velocity to get acceleration, you would end up having to take the antiderivative of acceleration to go backwards to velocity. So we got that. So, by the way, now we could go in and we could answer total distance by just taking the absolute value of t squared plus 6. By the way, t squared plus 6 is never negative, so you can just shed the absolute values right up front. And you can also find that the displacement, which is the same thing. So now we have the information that we could use to do parts A and B. I'll let you do parts A and B on your own. But now let's go on to part C. To find a position function, we have to do just like we did, we rewrote acceleration as dv dt. We're going to have to rewrite velocity as change in position with respect to time. I'm going to let P of t represent position at time t. So velocity is derivative of position with respect to time equals t squared plus 6. Once again, we are going to solve this differential equation using separate and integrate. So here we go, separate. P's on the left, T's on the right. That includes dt. That concludes the separate portion of separate and integrate. Now we take the antiderivative of both sides and we do the sponge bobbing routine. It's P plus C1 equals t cubed over 3 plus 6t plus C2. And so now we have P equals 1/3 t cubed plus 6t plus C3. So I'm going to pause the camera. I want you to use the initial condition that at time 2, the position is 100. Whoops, they're using S. Change that S of 2 to P of 2. Okay, the position at time 2 is 100. I would like you to use that initial condition to solve for this other C3. I'm going to pause the camera. When you're done finding the constant of integration based on this initial condition, then unpause and see how we did. Okay, I'm back. So to solve for C3, I put 100 in for the position and 2 in for time. Giving me 100 equals 2 cubed is 8/3 plus 6 times 2 is 12 plus C3. Multiply both sides by 3 to get 300 equals 8 plus 36 plus 3C3. And simplifying, I get 300 equals 44 plus 3C3. When I subtract 44 from both sides, I get 256 equals 3C3. 60 and 256 divided by 3 is 85 1/3. So I get C3 is 85 1/3. So that means that my position formula, now that I finally found the member of the family that corresponds to this initial condition, the formula I'm going to use to answer part C is that P of T is 1/3 T cubed plus 6T plus 85 1/3. And to answer part C, then, all I have to do is evaluate this function by plugging a 7 in for both of those T's. So whatever P of 7 is would be the answer. Now, I'd like you to go to this next page then, where we did some work on this, but we didn't finish it. So this is going to tie together a lot. We use this problem to introduce the fundamental theorem of calculus, also called the evaluation theorem. But now we're going to actually figure out what's going on. So let's take some time here to read the problem. It says the acceleration a of t of an object moving back and forth in one dimension. So this is called rectilinear motion. We have, let's say, an x-axis, and this object, this particle, if you will, reductionistically speaking, don't get carried away thinking that everyone's just like a particle or nothing more valuable than a particle, but this particle is moving sometimes right, sometimes left. And the acceleration of this particle is given in the graph below as a function of time in seconds t. So this is the acceleration function, the velocity of the object at time 3. So they're giving us the initial velocity at time, or the velocity at time 3, find the velocity at time 18. Well, here's the idea. Final position equals initial position plus the net change in position. Final velocity is the initial velocity plus net change in velocity. Final acceleration is, the bottom line is that it doesn't matter whether it's position, velocity, or acceleration. We're going to use the idea that final equals initial plus net change. So this is final velocity. You could even call it V of t final. Put a little subscript of f in there. V of t final equals V of t initial plus the definite integral from t initial to, let's make that t final also, of v prime of t dt. We had written that, we've done something similar of t initial to t final. Okay, so they're asking us to find the velocity at time 18. So time final, that's t sub f, and they gave us, how about we make this t initial? 3 will be t initial. So the velocity at time 18 is found by taking, that's the final, let's take the initial. Let's take the velocity at time 3 plus the integral from 3 to 18 of v prime of t dt. Oh, happy day. Velocity prime is acceleration. So all we have to do to find v of 18, the velocity of time 18, is to take v of 3, which is negative 35, plus the area under the curve from 3 to 18. Now that consists, from 3 to 18, consists of a trapezoid, a rectangle, a triangle, and another triangle. The trapezoid will have positive area, the rectangle will have positive area, the triangle will have positive area, and this triangle will have negative area. So we're going to add up 3 positive numbers and a negative number to snag this. Okay. I better find the height of golf ball 3 on this function. So this is going 4 4 to 10, I'll bet I can eyeball it. Because it looks like 0, 3, 6. It's going to be the average of 4 and 10. It's going to be 7. It's going to be a 7. 6, 10. I mean, you can find the equation of this line because you took algebra 1 and you know how to find the equation of the line. Pass it through 0, 4 and 6, 10. And you could plug 3 into that equation. If the input is 3, you could calculate the output. But just by using symmetry, it's got to be 3, 4. It's got to be 3, 7. So the area of a trapezoid is average of the bases times the height. I'll say this base 3 plus 7. So it's going to be, you know what I'm going to do? I'm going to call this area number 1, area number 1, area number 2, 3, and 4. Let's do these separately. Area 1 is average of the bases at 7 plus 10 over 2 times the height. We'll say the height is like that, it's 3. That's area 1. Area 2 is a rectangle. This, by the way, 3, 6, 9. There should be a 12 there. It's going by 3s. So that should be 6 by 10. It's a 6 by 10, or 60. By the way, what is this? 17 over 2 times 3. Are you kidding me? 17 halves times 3. So that's 30, 51 over 2, or 26.5. I mean 25, yeah, so it's 25.5. Okay, so it's 25.5. 60, area 3 is a triangle, so it's 1/2 base times height. We'll say the base is 3 and the height is 10. So 5 times 3 is 15. And then area 4 is a negative number. It's negative 1/2 times the base is 3 times the height is 8. Or you could just say 1/2 times 3 times negative 8. Make that positive. That shows you why it's negative area. So that's going to be a 1/2, it's negative 12. So it's negative 35 plus 25.5 plus 60 plus 15 minus 12. And I'm going to type those numbers into my calculator so I don't make a mistake. So I'm less likely to make a mistake. So I think the answer to this problem is negative 35 plus 25.5 plus 60 minus 12, 38.5. So that's what I got for my answer, 38.5. Any questions? If you have a question, just text it to me. If you don't know my number, just pick a number at random. It might end up being my phone number. Now, go to the other handout, which is, this is handout 5.4b if you're taking notes on Surface Notes. No, I'm sorry, 4.5. 4.5b. 4.5b, open that up. It should look like this. Okay, this is more final equals initial plus change. Final equals initial plus change. So we're almost done. And I'll tell you what the homework is after we do a couple of these. Okay, so velocity, moving in recto. Okay, so here's velocity. Position of the vehicle is given by that. And determine the position of the vehicle at 15 seconds. Multiple choice. Okay. Well, I did the first one for you. I'm using, instead of P for position, I'm using S for position. Physicists sometimes use S instead of P for position, not sure why. So final position equals, because I mean the numbers they're giving us, we have to go with them. So at 3, so initial time is 3, final time is 15, so final position equals initial position plus this. And S prime is, derivative of position is velocity. So S of 15 would be found by taking S at time, the position at time 3, which I believe was given, 24, plus the integral from 3 to 15. S prime is velocity. They gave us velocity. So it's just 4 plus 9 sine of 2 pi t over 20 dt. And I believe I've already typed in what that is. Sure enough, if you type into your calculator 24 plus math 9 of 4 plus 9 sine of 2 pi t over 20, you get 88.839 approximately. So that's S of 15 is approximately 88.839. Let's see what the units are. And it looks like the units are feet. Yep, so the final position in feet is given right here. Okay, now I did part A. See if you can do part B on your own. I'm going to pause it, see if you can get rounded to 3 decimal places the answer to part B. You may begin. Okay, I'd like to show you my progress here. I said V of 15 is, now V of 3, I just take the velocity function that they gave me and put a 3 in, so that'd be 4 plus 9 sine of 2 pi times 3 over 20. Now I need V prime of t, which means I have to, oh, by the way, this is a calculator problem. On the AP test, this would be a calculator problem, so I'm just showing you how to best use your calculator to most quickly get the answer. This didn't take me much time. I'm just trying to type in the derivative. I had to take the derivative in my head. The derivative of 9 sine of that would be 9 cosine of the blob times the derivative of the blob, which is 2 pi over 20. I don't have to use t on the calculator. I could use x, but I want to show you by just pressing alpha t, I can use t also. Sometimes it's to your advantage to use the letters that are in the problem. Trust me on that. So I typed it in like this, and it doesn't take long to type in. The answer is 38.030, where O means 0. So let me snag that again. Oh, lost it. And will it ever come back? Oh, I found it. Okay, so dragging it into the document, which is right here, enables me to write it down. So it looks like the answer to part B is V of 15 is approximately 38.030. And that would be feet per second. Feet per second. Units are required. Now, what if they said A of 15 equals A of 3, etc.? And I just want to see what the next one is. Oh, yeah, okay. So how am I going to find the acceleration? Well, I would have to take to find acceleration of 3, I'd have to take the derivative of velocity to get acceleration. And to find acceleration of 3, I'd have to do the same thing. I'd have to take the derivative. Remember, the derivative of acceleration, is, so I'd have to take the derivative of this thing again. So that's kind of tedious. I think you'd be able to pull it off. Let's just go on to part B. Here it says the acceleration in feet per second squared of a vehicle moving in rectilinear motion along the x-axis as a function of time t is given by the function a of t equals 9 natural log t. Okay, the velocity of the vehicle in feet is given by that. Okay, determine the velocity of the vehicle at 15. Okay, friends, this is one that I believe you can do. So your homework, the other homework assignment for Friday, is to do part B. That's a practice problem. So this will be a paper submission. Do this problem on a separate sheet of paper, show all your work, round your answer to 3 decimals. I want you to show me the calculator setup, and that's due on Friday. Now, we're not done. In fact, you know what? I'm going to have you do part of problem C also. I'm going to kind of get you going on part C to set you up, but then you can finish part C. So your homework is going to be to do parts B and C. But let me help you get going here on part C. Part C says here's the acceleration function. By the way, this is AP level. This is kind of like what you see on the AP test. We've seen a lot of these table problems. So here's acceleration, the velocity of the vehicle. So they've given us the initial velocity, use a Riemann sum to approximate the velocity at time 15. So the idea is that when you're doing part C, start out with 3 boxes. Final velocity equals initial velocity, right Riemann sum. Okay. Initial velocity plus not total change, but net change in velocity. Okay? Final velocity would be the velocity at time 15. The initial velocity will be the velocity at time 3, so the change would be the definite integral from 3 to 15 of v of t dt. Now, I'm sorry, of v prime of t. Well, happily, v prime of t, v of 15 equals, v of 3 is given as 25. The derivative of velocity is acceleration, so oh happy day, we have acceleration information, but we're going from 3 to 15. Whoa, our table goes from 3 to 15. So how many rectangles? It's like there's going to be this will be the first rectangle, will be 1 unit wide. The second rectangle will be 2 units wide. The third rectangle will be 3 units wide. The fourth one will be 2 units wide, 2 units wide, 2 units wide. So not all the rectangles have the same width. So there it is. You have to finish it from here. This piece will be the right Riemann sum based on the table. So finish up, do part B and finish part C. Paper submission for Friday. Enjoy the rest of the middle of your week. Have a good night.